Open a new file in Abaqus. Rename the default model Heat Transfer. Create a new part called Block, which is a 3D deformable solid extrusion, and set the approximate size to 5. Sketch the profile using the Create Lines Rectangle tool. Dimension it using the Add Dimension tool. Give the extrusion a depth of 6 meters. Let's create a material. In a steady-state heat transfer analysis, the only material property required by Abaqus is the thermal conductivity. We will use the material copper. Set the thermal conductivity to 401 watts per meter per degree Celsius, which is in the appropriate units since we are using SI with length in meters, and we will specify our temperatures in degrees Celsius. Moving on to sections, let's create one named block section, which is of type solid homogeneous. Ensure that the material is set to copper. Now assign the section to the part. Create a dependent instance of the part in the assembly. Now we shall partition the block. Partitions, as you know, can be created on a part or on an instance of a part in the assembly. In this case, the part has been instanced into the assembly as a dependent part instance. You may already be aware from earlier tutorials that a dependent part instance cannot be meshed in the assembly module. It is the part that must be meshed in the part module. Similarly, you cannot create a partition on a dependent part instance in the assembly module. You need to partition the part in the part module. If you try to use any of the partition cell tools in the assembly module, Abaqus will give you an error. So the first step to creating the partition is to switch to the part module using the module drop-down list. We shall create the partition by creating a datum plane where we would like the partition to be, and then use this datum plane to partition the block. Let's use the Create Datum Plane midway between 2 points tool. Abaqus prompts you to select the first and then the second point to create the partition. You might need to rotate the view in order to select the second point. Abaqus will generate the partition midway between the 2 points we selected. Now let's use the partition cell Use Datum Plane tool. Abaqus prompts you to select the datum plane. Then click the Create Partition button. You see in the viewport that the part has been partitioned. We need to create a step for the heat transfer analysis. Let's name it Heating Step. The procedure is a general heat transfer. In the Basic tab, we see two options for response, steady state and transient. Transient is selected by default, but we wish to perform a steady state analysis, hence choose steady state. Abaqus informs you that the default load variation with time has been changed to ramp linearly over the step. This means that any load you apply will have a ramp amplitude, meaning that it will increase linearly over the duration of the step until it reaches its final value. If you were to click on Transient to switch back, Abaqus would inform you that the default load variation with time has been changed to instantaneous. Any load you apply will have a step amplitude, meaning that it will reach its final value instantaneously at the beginning of the step. So, to summarize, steady-state heat transfer procedures in Abaqus have a ramped load variation by default, whereas transient heat transfer procedures have instantaneous loads by default. This behavior can be changed. If you switch to the tab labeled Other, you see a section called Default Load Variation with Time with two options, Instantaneous and Ramp Linearly over Step. The user has the option of choosing one over the other right here. So if you select Steady State Response in the Basic tab, and Abaqus changes the default load variation to Ramp, you can open up the Options tab and change it back to Instantaneous. We will now apply boundary conditions to fix the temperature at two surfaces. Name the first boundary condition Constant Temperature Surface 1 and apply it in the heating step. This may strike you as surprising because in the previous tutorial videos, we have generally created our boundary condition in the initial step. While in many of them, it would have been equally valid to create the boundary conditions during the load step, my personal preference is to define them in the initial step, since I like to think of them as existing even before the loads are applied. However, this is not possible in this procedure because Abaqus will not let you apply any non-zero boundary conditions in the initial step. In previous tutorial videos, our boundary conditions have involved fully or partially constraining the instances by setting either a few or all of U1, U2, U3, UR1, UR2, and UR3 equal to 0, depending on which degrees of freedom we wish to constrain. However, in this case, we wish to set the temperature boundary condition to a non-zero value, hence we cannot apply it in the initial step. If you try to select the initial step here, Abaqus will not allow you to specify a magnitude for the temperature when you click Continue, and will instead set the magnitude to 0 without any option to edit it. Set Type for selected step to Temperature. Abaqus prompts you to select the regions for the boundary condition. Set the distribution to uniform and the magnitude to 400 degrees Celsius. Similarly, create another boundary condition named Constant Temperature Surface 2. Set this one to a temperature of 350 degrees Celsius. We can now create the heat flux load. Set the step to heating step and the type to surface heat flux. Abaqus prompts you to select the surface for the load. Select the surface in the viewport and then click Done. Since we are using SI units with length in meters and temperature in degrees Celsius, consistency requires that the heat flux is specified in watts per meter squared. We will give it a magnitude of 5000. We leave the distribution at uniform, which is the default. If instead you wanted to create an analytical field represented by an expression, you could choose User Defined and click Create. We also leave the amplitude set to the default of ramp, which, as mentioned before, will linearly increase the heat flux from 0 to 5000 watts per meter squared over the analysis step.